So the homework 12 is due by 5 o'clock that day, flood control and groundwater, and there's a pretty detailed explanation on how to do the flood control problem. I think both in the recorded lecture that we had from last Friday's class, but then also on the assignment itself, there's a link that takes you straight to the part in a previous lecture where that's demonstrated. For our final on Friday the 29th, remember I've mentioned before that you should bring in all of the software packages on your computer because we've got 2 hours and I plan to lengthen the exam accordingly. And you can bring in a page of formula and problem solving notes, but that shouldn't include any kind of conceptual or definitions because I'd like you to answer the concept questions just from your own understanding and memorization of that material. And so the point breakdown will be about 1/3 conceptual questions, 2/3 problem solving and computer work, with an added emphasis on the more recent material that you haven't yet been examined on. Any questions on the announcements before we continue talking about groundwater? All right. So this is where we left off Monday. We were working on the confined aquifer example. And just to refresh your memory, this curved surface isn't actually the water surface, but it's a representation of the piezometric surface. That is the height that the water would rise to if we had an observation well at a given location. And so the water itself is limited to the aquifer, which is confined at the top and the bottom. So the physical elevation of the water won't go above that upper confining layer, but the pressure at that upper confining layer is high enough that if we punctured it, then the water would rise up here to the piezometric surface. And so the drawdown of that piezometric surface is what causes the water to move towards the center location in that well. It's flowing radially towards the center, which is the well, and the driving force is the reduction of that piezometric surface. So in the previous example, we found the flow rate in part A of this question. Let me give you a handout that has those details from last time, namely just the flow rate. Because what we're going to do now is find out what is the water depth at the well itself if we know the diameter of the well. Okay, so previously, what did it say our flow rate was? Is it 506 cubic meters per day? I've just given out all the handouts. I don't have one anymore. Is it 506? Okay, so when we solved the first part, we substituted into this equation, and remember that the transmissivity T is the thickness of the aquifer multiplied by the hydraulic conductivity. So we had T, we had H1 and H2, which is the height that the water would rise to if we had an observation well at a given radius, where location 1 has to be the closer one, location 2 is further away. So now for the second part, what I'd like you to do is get some practice with this formula, calculating the depth of the water at the well. Now, it says that the well diameter is 0.5 meters. So what that means is we're going to set location 1 to be the outer casing of the well. So, in other words, R1 would just be the diameter divided by 2. And the unknown is going to be H1. So, we know the flow rate from previously, 2 pi, that's a constant. Transmissivity is the hydraulic conductivity, K, multiplied by the thickness, B. So that's known. H2 can be either of those other distances. And so location 2, I've just told you that location 1 is going to be the well casing itself. Location 2 just means some spot further away where you know both the radius to that location and also the H value at that location. So we could choose either the spot where it is 40 meters away, or we could use the spot where it's 85 meters away. Either one is going to ultimately, if we use the corresponding R value and H2 value, we're going to be able to solve for H1. So H1 is the unknown. Let me pause for a moment, give you some time to calculate that. Just as a reasonableness check, we do know it should be shallower than either 14.31 or 13.85, because that was saying how tall the water was, far away, a little bit closer, so it should be less than either of those. Okay, so here's the calculations from last time where we had found that the flow rate was 506 cubic meters per day. Now for this one, we're going to use that flow rate and try to back calculate what will be the height of the water at the well. And the water height at the well will just be whatever the height of this piezometric surface is at the radius of the well. Because once that piezometric surface intercepts someplace the water can actually go, then the water is rising to that level. So remember, what I said was that if we punctured this confining layer, then the water level would rise to some elevation representative of the piezometric pressure at that radius from the center line. And that's exactly what's happening at this production well. Is not only are we taking water out at that location, but it is punctured the confined aquifer and the water is rising to a certain height there, reflective of the piezometric pressure. Okay, so you can just see we've kind of rearranged the equation here to solve for H1 in terms of H2. So it's H2 minus the flow in the well multiplied by the logarithm of the ratio of the two radius, and then divided by 2 pi transmissivity, which is K times B. So regardless of whether you used your location 2 to be where the radius was 40, or if you used where the radius was 85, and then had the H2 value accordingly, I think what you ought to get is 10.75 will be the height above the lower confining layer that the water rises to at the well. So if the well was a little bit wider in diameter, then the water level would rise higher because it would be intercepting this piezometric surface further away from the center of the well's axis. So that's the confined aquifer. Are there any questions about that? Things are similar, but maybe deceptively similar, because there's a really important difference when you have an unconfined aquifer, a really important difference in the formula. So here's the unconfined aquifer, and it's really easy to look at the equation and say, oh, that's the same equation. But it's not. Instead of transmissivity, this unconfined aquifer equation is just using the hydraulic conductivity. So the first difference is that the thickness of the aquifer isn't included as a parameter out here in the front, because where the water is changing in an unconfined aquifer. It's not just the piezometric surface that varies as you move radially away from the production well. It's actually the physical height of the water. So B, which in this previous example, B was just talking about, what is the thickness of the region that has water? B was a constant in a confined aquifer. But in an unconfined aquifer, where we don't have that top layer of clay preventing the water from rising to its full height, where it was just the piezometric surface that was being graphed out in this curve. Now this is the physical elevation of the water, and we can tell the difference here because it's got that triangle on it and those little ripple marks. So that's talking about the free surface of the water. Although it's below the ground, it's above that is the unsaturated zone, or the vadose zone as it's sometimes called, where the soil voids have some air, some water. Below this, all of the soil voids are full of water. So the first difference is we're not using a constant B, and a constant aquifer thickness. And because of that, think about the units of Q. What we're expecting for the units of Q are cubic meters per day, per second. It's basically volume per time. And that is what we had for the confined aquifer, because transmissivity was length squared per time. That was the transmissivity, and then we multiplied by H, which gave us length cubed per time. Now, in the case of the unconfined aquifer formula, if we're just using K, the hydraulic conductivity, that gives us length per time. So now we need to multiply it by length squared, or we need to multiply it by effectively an area in order to get cubic meters per day or cubic meters per second, in order to get a volume parameter on the left-hand side of the formula. So the second difference is that we're squaring these heights. So in the confined aquifer formula, it's just the difference in heights that goes into the equation. In the unconfined aquifer, it's the height squared minus the height squared. So the closer location would be 1, as it was in the previous. The further location is 2, and so the r's don't change in any sense. But I wanted to point out the subtle difference in the formula for an unconfined aquifer. So here it's what's called the phoratic surface. That means the actual free surface of the water, rather than the piezometric surface, which is just kind of a hypothetical where the water would rise to if we punctured the upper confining layer. Here's what the equation looks like in the FE reference manual. They give you the variable definitions. And here, they're making the point that your location 1 could be at the outside surface of the well itself. So here, this is just saying 2 is further away and 1 is closer. In the FE reference manual, they're saying 1 could be at the well casing itself. It doesn't have to be, but it can be. And so this will tell us the flow rate that is coming out of this unconfined aquifer if we're able to know the height of the water surface at 2 locations. Now, in this next example, I'm going to be introducing the idea of drawdown. You haven't yet calculated drawdown, and so this is like a trick question. Yeah, that's something that if the word question says calculate the drawdown at a certain location, unless you've had some practice with this, you might just calculate the height of the water surface without distinguishing between what is H and what is S. The variable S is the drawdown. That means the difference between where the water was initially before pumping began, and then where the water will be after equilibrium is reached due to pumping. So H is just the height of the water surface after the well reaches equilibrium. So here in this example, I'm asking you to get some experience in calculating drawdown. So what you're going to do in part B is you're going to calculate H, and then from that determine S. But before that, let's just use the given information to determine the hydraulic conductivity, because what we know is the flow rate through this well, 0.4 cubic meters per second. and the saturated thickness is 24. When it says the saturated thickness, that's referring to H. That is what is the height of the soil column that has water fully in all of the voids before pumping occurs. And so if you go far enough out, then if we're outside the radius of influence of the well, you get far enough away that cone of depression is no longer observable. And the height of the water above the lower confining layer here, 24 meters. That's a saturated thickness. Okay, so what we have is two different drawdown measurements. We've got a drawdown 50 meters from the well, where the drawdown is 1 meter, and 100 meters from the well, the drawdown is 0.5 meters. So remember, drawdown isn't H. Drawdown is S. And so the way that you calculate H, if you're given S and you're given this capital H, is that lowercase h is capital H. Let me write this on the whiteboard. Okay, so lowercase h at some location is capital H minus the drawdown at that location, S. So if we're saying the height of the water surface at location 1 is the thickness, the saturated thickness of the aquifer minus the drawdown at location 1. So you are given capital H and you're given S, and you need to calculate lowercase h to substitute it into this formula, where we're going to be rearranging that formula to solve for K. All right, so let me pause for a moment, give you some time to calculate the hydraulic conductivity of this aquifer. Let me just break in for a moment and show you the hydraulic conductivity calculations. Okay, so the first step is that we need to determine from the drawdown what is the height of the water surface at those two locations where we've measured the radius. So we've got some sort of a way to measure where the water surface is at compared to where it usually would be. That's what drawdown means, is that we have some indication of where the water surface was before pumping began, or we have gone far enough away from the well that we know the location of the water surface where it's no longer under the influence of that drawdown effect. So it was drawn down by 1 meter at a radius of 50 meters away from the center of the well that's producing the water, and then drawdown is 0.5 meters when we're 100 meters away. So you can see the H values for that. We're trying to find the hydraulic conductivity, so rearranging the equation to solve for the hydraulic conductivity, what you should get is 3.8 times 10 to the minus 3 meters per second. And that's pretty fast. So this is probably like a granular soil, like maybe something sandy, and most likely not a clay. Okay, so that was part A. Now, in part B, what we have to do is rearrange this formula once we know the hydraulic conductivity, we know the flow rate, and we're trying to determine the drawdown 5 meters away from the well. So we have a new location 1, and then we can either use the spot that's 50 meters away as location 2, or use the spot that is 100 meters away from the center of the well as location 2. Either one of those can be our further location, but the closer location is going to be R1 will be 5 meters, and we're trying to solve for H1, and then once you have H1, determine S1, the drawdown. I guess that's good enough. Okay, so I got a good question as I was circulating around about what should be the units of flow rate and hydraulic conductivity? Should it be cubic meters per day, cubic meters per second? And as long as you're consistent in both the length units and the time units, then you could leave, for example, the hydraulic conductivity as meters per second, but then you should have the flow rate in terms of cubic meters per second. So that's what I did, is I left it in terms of meters and in terms of seconds for both. And so if we just rearrange the formula and we're solving for H1, then it's going to be the square root of H2 squared. So what I said was, let's have location 2 be the spot that's 50 meters away. And the height of the water surface at that location 2 is 23 meters. So substituting that in, I got that the height of the water surface when we're 5 meters away will be 21.26 meters. And so then therefore the drawdown at that location is 2.74. 2.74 meters will be how depressed it is above where the height would be prior to pumping. All right. Well, that's all the time we have for today. The video that you'll have for Friday's class will be relatively brief. It won't be too lengthy. It has a little bit more of this this groundwater flow, and then I'll take some time to just throw a little bit of review information together. Nothing like exhaustive. It won't be everything we've done through the entire semester, but I just want to refresh your memory about a couple of key concepts that are really important, and maybe it's been some time since we talked about it and some time since you thought about it. So that recording for Friday will have kind of a dual purpose. But that's it for today. Thanks very much for a great semester. I'll see you for the final on Friday the 29th.